Okay, so let us go back to considering this infinite series, 1 over n squared. Then we get 1 over n. If you write them out, 1 over n, so 1 over 1, 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, and so on. So how does that compare to the function, right, 1 over x squared? So let me just draw an approximate picture of 1 over x squared. This is not to scale or anything. Okay, so when x is equal to 1, right, if you plug into this function, the y is, right, 1 over 1 squared. When x is equal to 2, the y is going to be, even though it doesn't look like it here, it's 1 over 2 squared, right? Okay, this is the function of y equals 1 over x squared. So, okay, let me just draw a few more. This is when it's 3. Remember, the y values represent, right, the 1 over x squared value. So here's 4, right? Let's say this is 5. Okay, so first of all, right, so I have 1. This right here, then this area here represents, right, because of the base is all 1, represents this value here. You can represent, right? So same here, 1 times, right, 1 times 1 over half squared. So that area right there represents the second value, right? And this area right here represents the third value, and so on, right? So these rectangles represent this infinite series. So how does that relate to the actual integral on this interval from 0 to infinity? So we don't want to do we don't want to compare with the 0 to infinity because that's an improper integral. Let's compare it with the integration from 1 to infinity, okay, on the function 1 over x squared. So this is definitely, right now, it's definitely bigger than, definitely it's bigger if you just omit this first rectangle. Okay, so if you omit that one, you can say n is equal to 2, right, to infinity for 1 over n squared. So then we can say if this integral is converging, right, this improper integral is converging, and since this is smaller, this will also converge. Okay, that converges. Okay, so we're saying, let me do a picture here. If the area under the curve here, if this area converges to a particular number, these rectangles, some of the rectangles will clearly be also converging. Okay, so how about, that's when I count it from 2. How about if I count it from n is equal to 1? Right, so that's equal to just 1 plus n is equal to 2 to infinity to 1 over n squared. That's converging. That's just a constant. So clearly, it's still converging. So what I just described here is the integral, the convergence test by integral. Okay, so here it is. If you have the function, right? So the function is same thing as the general term an if you put in n instead of x. Okay, then if this function is converging, then this is also converging. And what I just described here is exactly that statement. When that's converging, this is converging. Okay, so it says when this is diverging, the sum is also diverging. So let's see if we can argue that. Okay, so let me do the same thing here. Right, so before we had 1, right, 1, and when you had 2, it was, you know, 1 over 2 squared, provided that this, I'm using the exact same example. This is 1 over x squared, right? When it's 3 here, then this is 1 over 3 squared. Okay, so this is clearly under the curve, but I can make this over the curve, and here's how. See this rectangle here? Let's move it to here. Okay, so I'm moving the first rectangle to here. So second rectangle, let me move it to here. Third rectangle, let me move to here. Do you see how it's just a tiny bit bigger, right? Tiny bit bigger, right? This is There's just an overestimation here. So this will continue this way. So from this picture, you can see that the integral, okay, actually let me say the sum, the infinite sum, I is equal to 1 for an. In this case, it was, n is equal to n squared to infinity. This is greater than the integration from 1 to infinity, right? So the integration from 1 to infinity is this area down here. Okay, so it's clearly bigger for 1 over x squared dx. Okay, so you can see that using this analogy, if this is going to diverge, for example, if that does diverge, in this case it's actually going to converge, but if it does diverge, since this is bigger, it's also going to diverge. Okay, so that's the idea. Okay, so two very important theorems in determining if a particular infinite series is converging or not. If the equivalent integral is convergent. If the equivalent integration is divergent, the sum is also divergent.